Um, Great introduction, yeah, thanks. Welcome to our talk, A Brief History of iMessage Exploitation. I'm Sam. Unfortunately, Ian couldn't make it short notice, so I'll be covering his part as well. Now, for those of you who don't know, iMessage is Apple's messaging service that they use on their platforms. You know, when you send a message from your iPhone to your friend's MacBook or iPad, this is going over iMessage. And yeah, so this history or this story of iMessage security, I'm going to tell it in 3 chapters. I only have 40 minutes, so I kind of can't go into much detail. But every chapter, there's a blog post for it. You can find the link on the slide, and those slides end up on Twitter or so, and there you can find many more details. Okay, so why is iMessage interesting for security researchers? Well, if you as an attacker, if you are able to find and exploit a bug in iMessage, then you can basically remotely compromise kind of pretty much every Apple device without the user doing anything and without the user noticing. So it's really kind of scary, and I think it's very interesting to look into these attacks. But okay, so let's start with the first chapter. This starts in 2019 when my team at Project Zero, when we developed one of these exploits against iMessage. So I'll walk you through how this worked. Now, before we can exploit anything, well, we need a bug, right? But even before we have a bug, we need an attack surface. So some kind of software that we can supply input to that's going to process that input and where we can then look for bugs, right? So this is going to be the first step, finding an attack surface. How would you go about it? I think the straightforward way is you look at how iMessage works, like how an iMessage looks on the wire, right? So when you take one of these phones, you send a message. This here is what actually goes over the wire. It's called it's a property list. It's like the name of this format. It's Apple specific, but you can think of it like a JSON dictionary. I guess some of these fields, they will make immediate sense, like P, that's the participants. In this case, it's a two-person chat. T, that's the plain text message, like hello BlueHat. There's some what looks like it's HTML in there in the X key, but it's not really HTML. It's parsed as XML. It's kind of weird. Some UUIDs to identify this message. But what's really standing out, at least when we looked at this, is this ATI key, where it has some what's called an NS-keyed archiver payload in it. So it's like raw bytes that they then go into some other decoder. So what is the NS-keyed archiver? If you look into the documentation, it says NS-keyed archiver provides a way to encode objects and scalar values into an architecture-independent format suitable for storage in a file. Or, in this case, suitable for sending it over the wire. Now, this is a pretty powerful serialization format. It even supports cycles. So JSON, for example, it doesn't support circles, but this one does. So for here in this bottom image, you see like an NS array. NS is just the prefix they use for these objects. So you have like an array, contains a number and dictionary, and now the dictionary links back to the array. So you have a circle, and this you can serialize just fine with this format. So it's really quite complex. It has a lot of features, and so we immediately went into this as our attack surface. This looks complex. There could be bugs here. And now to make it even more, even nicer, we realized that one of these, so there were multiple payloads in these iMessages, but one of them was actually being decoded in Springboard. And Springboard is the main UI process, and it's unsandboxed. So what that means is if you find a bug in this format and you trigger and you can exploit it over iMessage, you immediately get code execution outside the sandbox. Like, it's done. So this looks really good. Let's go into that. So here's where we are. This is kind of, I'm going to like draw a picture of how these attacks work. They look like this. The colors are a bit ad hoc. So orange is something that's required. Red is the exploit flow. So we now have the attack surface. That's the NS-keyed unarchiver stuff. We have a bug. I didn't mention the bug. It doesn't really matter. We found a bug there. And we also have seen that if we can exploit it, we have unsandboxed code execution. So now we're in the exploitation part. And the first thing with these memory corruption bugs, the first thing we need to deal with is ASLR. What is ASLR? So it's address space layout randomization. Here's like a schematic of a process's address space. It can address everything from 0 to address hex 7, FFF, and so on. And we now need to find a certain mapping, like a certain object in the address space. It's called the DYLD shared cache. It's not really important what's in there. It's basically all the code libraries linked together. All the code is in there. And we need to find it to then continue the exploit, because we don't know where anything is in the process. So this is our next task. Now, why is this hard? So if you think about how kind of on an abstract level, how a typical memory corruption exploit works, it's these 3 steps that you have at the bottom. So the first step is you have to leak a valid address from the target process, right? You don't know where addresses are. You have to leak an address of something, and then you can figure out where some library is, for example. And so what you then do with that is you have your, what I call abstract payload here. For example, you might have a rob chain that is just offsets. So that is your abstract payload, just that rob chain with offsets into some library. Then you take that abstract payload and you instantiate a concrete one, if you so will, right? And so you do that by adding those offsets onto that address you leaked. And now you have a real payload that is valid in the target process and has like the correct addresses, and then you deliver that. This is kind of what you need to do. But for this to work, you need a communication channel between the target process and the exploit logic. Now, in some cases, this is not a problem at all. If you think about typical web browser exploits, there the exploit logic is implemented in JavaScript. And so it runs in the process that's being exploited. So, of course, you have a communication channel. You just read memory. It's the same process. But for us in iMessage, this is much more of a problem because there's, of course, no message that sends back addresses to like the attacker. So we have to figure out how to like communicate in a way that lets us infer ASLR addresses. So how are we going to do this? We will use something called delivery receipts. If you've ever sent an iMessage, you probably have seen something like this image here on the left. So a message, it can basically have 3 different states. It can be sent, delivered, read. Read meaning the user looked at it, delivered meaning it got to the device. The way this is implemented is that when the service, the daemon that processes iMessages, when it gets the message, it sends back another message to the sender saying, yep, this message, I got it. And then the sender marks it as delivered. Now this gives us an interesting oracle, because if during the processing of our iMessage, if the service crashes, then it never sends the delivery receipt. And so we have this like 1-bit channel that says, did it crash or did it not crash? And this is enough to break ASLR. So here's how. What we do is we construct a payload from the memory corruption bug that just like reads from some address that we tell it to, right? And we send this payload over iMessage to the target device, and then we check, did we get a delivery receipt or did we not? And if not, then the address was not valid, otherwise it's valid. And so we then we started some low address, maybe this one here, and it crashes. We don't get a receipt. That's why it's red. We check another one. And now we get a delivery receipt. So this address must be valid, right? And at this point, we just kind of do a binary search to find the base address. In reality, it's a little more complex, but the idea is exactly this. So in this case, we try the middle. That doesn't work. It crashes. Okay, so we take the upper half, again, go to the middle. This doesn't crash. Okay, lower half, right? And so on, and so on. And if you do this a couple of times, then you end up leaking the correct base address. Takes like 20 to 30 messages. So I think this exploit took maybe 3 to 5 minutes total. It's, I think, acceptable. Okay, so here's where we are. Right, we have the attack surface and the bug, and we've broken ASLR. And what we needed are all of these 4 things here. So we needed, what I didn't mention at all, we need this shared cache to be at a constant address across crashes, which was the case. Like the process restarts, but this thing is at the same address. We need the crash oracle. We do need some heap spraying, which I also didn't mention. And we need to be able to make repeated attempts. So back then, you could just send a message, get the service to crash, 10 seconds later it would come back, you try again, right? So you have a lot of attempts. So this is where we are. Final step is we need a PAC bypass. What is PAC? Pointer authentication. It's a newish hardware security feature on Apple's platforms. The idea is that you can cryptographically sign pointers and then verify that they are legitimate, right? And so this effectively breaks rob and job and these kinds of standard exploit tricks because they all rely on you faking or creating your own pointers into code. Yeah? So at the bottom, you can kind of see how PAC works very briefly. Like you take a normal pointer, the top bits are all unused. You run it through one of these PAC sign instructions, and that puts the signature in the top bits. And then if you want to use this pointer, you first run it through one of these authentication instructions. If that succeeds, if the signature is valid, then the top bits are cleared to 0, the address is valid. If the authentication fails, the top bits become some garbage, and if you then try to use it, you crash. Yeah. So this breaks rob. But if you think about it, really, arbitrary code execution isn't necessary for you, right? Like, whatever you would want to do after your first stage payload, all the functionality is there, like all the syscall functions or so, all the ObjectiveC methods, it's all there. So really all you need to do is figure out how to just call existing methods. And this is not too hard with ObjectiveC. ObjectiveC is kind of very dynamic and the runtime around it. And so one of the objects that was very convenient back then is NSInvocation, which essentially represents like a bound function call or bound method call. So it looks like this, maybe a bit weird if you've never seen ObjectiveC, but this makes an NSInvocation, then sets the target object to foo, then sets the selector, which is the method, to bar, and then if you call invoke on the invocation, this calls foo.bar, right? And so if you control one of these objects, you can call whatever you want. So you win. And so this is the full exploit. This is how it looked like in 2019. Yeah. So first chapter is over. Let's go to the next one. So what happened afterwards? We did this 2019, mid-2019. We sent all of this to Apple, and they got very busy fixing stuff, right? And so this is the next chapter, all the things that Apple did afterwards. So one of the very first things, and this happened, I think, only days after we sent them the stuff. Well, they fixed the bug, of course, but they also did a lot of attack surface reduction. And this is really powerful because not only does this make this bug unexploitable, it makes all other bugs that are like in the same area unreachable. And so they yeah, they basically blocked a whole bunch of this NS archiver attack surface in iMessage. So that's really nice. Let's look at what else they did. One of the biggest changes is they did some re-architecturing for iMessage, and they introduced something called BlastDoor, or Messages BlastDoor Service, which is essentially a super tightly sandboxed process that sits in between the iMessage processing and does all the parsing. So IMAgent here, that's the daemon that gets the incoming iMessage, and this pretty much directly forwards everything to BlastDoor. BlastDoor does all the parsing, all the plist parsing, the XML parsing, the NS keyed archiver parsing, whatever is in there, and then sends the result back to IMAgent. It also has high-level logic implemented in Swift, which is kind of nice. It's a bit more of a safe language. But also, like besides sandboxing stuff, this also breaks the crash oracle, because no longer is, like, the sending of the delivery receipt is decoupled from the it's no longer happening in the process that crashes, right? So if you send a crashing payload, BlastDoor crashes, but IMAgent is the thing sending the receipt, so this no longer works, right? And so they fixed this box here, and this already breaks the ASLR bypass. But that's not all. So the next thing they did is the constant address of the shared cache, that's gone. They implemented some shared cache resliding. It's actually quite interesting. It seems to specifically look for this attack where you kind of probe memory around the shared cache to figure out where it is. And when they detect you doing that, they just re-randomize the shared cache. So this technique is also broken. And also they stopped you, they try to stop you from subsequent, like crashing a service and then having it restart quickly by introducing something called exponential throttling. The idea being, well, if the service crashes once, it restarts 10 seconds later, crashes again, 20 seconds delay, crashes again, 40 seconds delay. This goes up to 20 minutes. And so very quickly, you only get one attempt every 20 minutes. And so this exploit from 2019 wouldn't have taken 3 to 5 minutes. It probably would have taken a few hours. So still not terrible, but yeah. OK, so this already looks pretty solid. But then they also tried to fix all of these techniques. So the 2019 exploit, it would just fake these NS invocations objects in memory. But they fixed that by signing them with PAG. So there's a PAG signature in these classes now. You can no longer just create these things from scratch. They also did some hardening of these NS invocations. So that also doesn't work. Sorry. Right. So this looks pretty solid, right? Like kind of every aspect of this exploit, with the exception of heap spraying, which I think still works. All of the other stuff is fixed. And so you would expect a new exploit, like it would have to be quite fundamentally different, right? All of this is gone. And yeah, it was quite fundamentally different. So last year, Citizenlab found an exploit titled forest entry, which was actually used in the wild, an iMessage exploit. And they found traces of it. They found a file containing the exploit, basically, and they gave it to us, and we looked at it. So we didn't write this exploit, but we analyzed it. Again, I'll walk you through how it works. Again, we have to start with the attack surface, because the previous one is gone. Okay. So I showed you this image before, right, where like BlastDoor came in and how the parsing works. It's not like it was obviously a simplification. One of the other things that happens is there's another process called IM_transcoder agent, which does some image transcoding, for example. So this one is important. Now, what iMessage wanted to do is when you send a GIF file, so like an animated picture, what they wanted to make sure is that it effectively looped forever, right? So it wouldn't stop like repeating itself. So here you just saw the left image just like repeated once, and the right image keeps spinning, and so on. Now in the GIF file format, the way you say this is supposed to loop forever is you set some loop counter to 0, right? So you see kind of a hex dump of these two files. The only difference is one of them has a 0, which means infinite repeats, and one has a 1, which means 1 repeat. So that's what they wanted to implement on the receiver side. So you get a GIF incoming, they would try to set this loop count to 0. The way they did it is there's a helper function that would be called by iMagent when it like downloaded those attachments or those images. It would call a function called copy GIF from path to destination. And this actually ended up running in this IM transcoder agent. And this transcoder agent, it would call a method like something read file properties, blah, 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 with updated loop count, and then gave it a loop count of 0, right? And so this kind of seems simple, like, I mean, just, you know, read the file, set the loop count to 0, write it back. But funnily, or maybe not so funny, this is an actual stack trace from the exploit crashing, so from it failing. And well, you see it starts in iMessage. It starts exactly in this copy GIF from file and so on, goes to the read file properties. It then goes into image.io, which is their image parsing library. And then it goes into core graphics, right? And you kind of see it's like starting to do PDF stuff. Why is it doing PDF stuff? And then it's going into something called JBig2, which is a compression format used in PDF. So what you see here is that this seemingly harmless call of like just, you know, take this GIF, make the loop count infinite, this ended up doing PDF parsing. So it's kind of like Iceberg attack surface, right? Like you see the top, just this top bit of like, this is just a bit of a, you know, file copying. No. PDF parsing, all kinds of stuff is happening under the surface. How much stuff is happening under the surface? So here's a list of all the supported file formats that image.io will parse for you, right? And so the trick here is that, I mean, the reason this happens is because image.io, it tries to auto-detect the file format. So even though you send something ending with .gif, image.io will look at the header and determine, no, this is a PDF. I know how to work with this, right? So yeah, this is maybe a bit surprising, right? I mean, you see the, I guess, typical image formats, JPEG, PNG, and stuff. But just for fun, raise your hands if you know what .psd is, the top right. Okay, it's pretty good. So it's a Photoshop file. Raise your hands if you know what ASTC is. Okay, that's like one person. Adaptive Scalable Texture Compression. I don't even know. Anyone know what MPO is? No, okay. So, I mean, I didn't either. Apparently, it's some kind of image format used on Nintendo 3DS, where you could like, because it has two cameras, you can take like some kind of stereoscopic image, and yeah, I don't know. So it's pretty crazy. But the point I want to make here is this is not a like Apple-specific problem, right? Like this is how we develop software in a way, right? Like if you are writing a library, you want that library to be as useful as possible. And so if you're writing an image library, that means you want to support as many formats as possible for your users to be really useful. But then this just ends up being this gigantic attack surface of like these dozens of file formats, right? Okay, so anyway, back to JBig2, right? So that's the compression code in PDF. This is the bug that was ultimately exploited. it's not really that interesting. It's kind of a standard heap buffer overflow coming from an integer overflow. So you have this num symbols integer. You want to allocate some buffer to hold all the, I don't know, symbol dictionaries or so. So you first figure out how many are there, so you add up all the dictionaries. This thing ends up overflowing from like 4 billion to 10 or whatever. You allocate a buffer for 10 symbol dictionaries, and then you copy 4 billion into it, right? So that, of course, corrupts memory. So we are here again. Looks kind of familiar, right? We have a new attack surface. We have a different bug. We know where we're going to end up with. We're going to end up in IM transcoder agent if we can exploit this. And again, we have to bypass ASLR. And this time we have to do a different thing because the last approach was completely fixed. So the first thing we're going to do is we will, what we just call unbounding here, will make more memory available to JBIG2. So JBIG2, it operates on bitmaps. You can supply it operations to perform on bitmaps. We'll see that in a second. And in memory, a bitmap looks like this. vtable, so on, so on. And then there's a width and a height, right? And so if you just overflow, corrupt one of these bitmap objects with this heap buffer overflow, you end up corrupting the width. Now the bitmap looks really large, and you can perform your operations on kind of all of memory. So this is a fairly standard exploitation trick. Just make some buffer look really big, and then use it. So the next thing is we need to understand a bit more about what JBIG2 is. So it's a compression algorithm designed originally for, I believe, kind of black and white scans of documents. And one thing it can do, it can figure out similar looking pixel patterns, like it might identify all of these E's as being similar in this document, and it can group them together. And what it can then do is just take one representative, like the one E, and replace all of the other E's in the document with this one, right? And so now you no longer need to store 6 E's, you just need to store 1. That's kind of neat, except that this can go horribly wrong if it like replaces one character with another that looks a bit similar, and I think this happens, or happened. And so the way you can fix that problem is by just kind of computing the difference between the reference or the substituted E and the original E, right? So here, left E, that's the reference one that's going to substitute the others. The middle one is the real E. So you compute the difference, you store the difference, which has less entropy, so it can be encoded more efficiently. And then when you decode or decompress the stream, you apply the difference again to the substituted one. So in this case, this just needs an XOR operation. XOR is not the only one. JBIG2 supports these 4 kind of fundamental logic operations and or XOR XNOR. Well, if you have these 4 gates, you can build other gates, right? Like if you, for example, combine an AND with an XOR with a constant of 1, that gives you a Nand gate, right? The XOR is a negation, so this makes a Nand gate. And now, well, a Nand gate, that lets you build all kinds of stuff. Like you can kind of build every circuit from Nand. There's a website where you can go to where they teach you how to build a like full-scale computer just from Nand gates and then write Tetris for it. What they don't tell you in this course, but what I can tell you is you can also take Nand gates and like build an IM transcoder sandbox escape from it. Yeah. So Nand is really powerful. This here is an actual gate that was used in the exploit. So this is an adder built right from these basic circuits. And so what this now lets you do is, because we have unbounded the JBIG2 stream, right, we can now add arbitrary stuff in memory together and like perform logical operations on other parts of the process memory. So how does this help us with ASLR? Let's go back to this slide. Remember from before? Before we needed this communication channel, right? Because the exploit logic was running on the server, on the attacker's machine, and the target process was on the device. But now with these JBig2 like virtual machine thing, really what we're doing is we're now running the exploit logic also inside the target process, right? It's really quite similar to the browser exploit where you would write all of the exploit logic in JavaScript and run it in the attacked process. And here we're not using JavaScript, we're using JBig2 virtual machine something, but it's effectively the same thing, right? And so this means we no longer need this communication channel. Yeah, so here's where we're at. We have the attack surface and the bug, and we break ASLR essentially by implementing a mini CPU from JBig2 compression operators. Yeah, it's definitely not like a weekend CTF project building this thing. So that's I think it's quite a lot of effort, but yeah. So what's left is the pack bypass. I'm just going to show this slide. I mentioned it before, like ObjectiveC is really quite dynamic, and this runtime, it like really lets you do a lot of things. Like you can add methods to existing classes at runtime, stuff like this. And here's another class that you have available called NSExpression. And if you just kind of scroll down in the documentation, it literally says, since macOS whatever, function expressions also support arbitrary method invocations, right? I mean, that's all we've been looking for. So this is a kind of easy substitute for the NS invocation stuff. This is again how you can call arbitrary stuff. This is how the final thing looks like. So yeah, we're creating these NS expressions. Remember, we can't fake them. We can't just create our own NS expressions in memory anymore because Apple added the signature to objects. You can make your own. What you can still do, and what this exploit does, is it just deserializes them. So remember the NS archiver, it can decode arbitrary objects. So if you can pass input to one of these decoders, you can just create every object you want, right? You can like deserialize NS expressions. It's going to work. So that's how this exploit got this object. Right, and yeah, here's the kind of end of chapter 3, the final exploit flow. So I think the story continues. I did take a brief look yesterday, and from what I can tell, Apple has already again done some attack surface reduction and removed a lot of this, like this copy GIF stuff seemed to be completely gone. So I expect there to be more changes. Will be interesting to see. Right, so let's go to the conclusion. I think there are kind of two main points that I want to make. The first point is, if you do make the right hardenings, right mitigations, they can make a big difference, right? Here, we saw that the old 2019 exploit was kind of fundamentally broken. The new exploit had to be written from scratch, go a completely different route. If you compare that with typical browser exploits, they kind of all look the same, right? They will all pretty much do the same thing, and they have been doing that for the last couple of years. This one here is like completely different thing. On the other hand, right, the fact that this second exploit was possible at all, it's good to keep in mind. I think we should assume that if you have memory corruption, it's probably still exploitable in some way. I mean, when we did this research back in 2019, I think many people were saying that these kinds of bugs in iMessage, they can't be exploitable. But yeah, now we've seen it at least 2 times, so it's really, like, memory corruption is really still very powerful. Maybe 2 smaller points here. So I think sometimes it can be quite hard to reason about where a specific piece of code runs. So we've seen this here. We had this BlastDoor process, but somehow this parsing still ended up being an IM transcoder agent because of, whatever, the GIF transformation stuff. It was also similar in 2019 where one of these payloads was decoded in Springboard, which seemed really weird because it's unsandboxed. This is maybe one interesting thing. And the other is like, look out for this hidden attack surface, right? Like this, it looks very, not dangerous, like just this copy GIF thing, but then it throws you into this huge sea of like image formats that it will suddenly parse. So yeah. Yeah, and that's the end of my presentation. Thank you all for listening. I guess we do have 4 minutes if there are any questions, but otherwise I'll be around. Feel free to find me, ask me whatever's on your mind. Thanks.